And let's get the PowerPoint up. And we will pick up where we last left off, which was redox reactions. All right, so on Tuesday, we looked at how to determine redox numbers for individual carbons. And we just looked at, one carbon in a compound. Are we seeing a oxidation reaction or are we seeing a reduction reaction? And now the next thing we're going to do is we're going to take those skills we learned on Tuesday and we're going to apply it to a whole molecule to try and determine the oxidation state of a whole molecule. So let me show you how this is done. First, we do the same thing that we did on the previous problem, in that we want to just determine the oxidation states of each carbon in the compound. So if you remember, we have some rules. Hydrogen always has an oxidation state of +1. Oxygen nearly always has an oxygen or a redox state of -2. It can be -1 on occasion, but it's usually -2. So with that in mind, I'm going to figure out what are the redox numbers for compound A. So we have 3 hydrogens. So overall, that's +3. So this carbon has to be -3 for that to balance out. Here, the center carbon is connected to an oxygen, 1 hydrogen, and another hydrogen. This isn't charged, so overall, the oxidation state of the carbon in the center will be 0. Then the carbon on the right. We have +1 from this hydrogen, -2 from these oxygens. And then we have 2 hydrogens, so that's also +2. Again, this carbon, this group is not charged, so everything has to equal to 0. So this carbon would be -1. And then when we're comparing different compounds, the easiest thing to do is just look at the carbon's oxidation numbers and add them up. So when I do this, the overall oxidation numbers of this molecule for carbon would be a -4. And so that's how we can kind of look at how reduced something is or how oxidized something is. And we'll see when we go through metabolism how these numbers can change from the very start of the metabolic process all the way to the end as we do our chemistry. So I want to just begin right now and take a few minutes and see if you can determine what the redox numbers are for B, C, D, and E. So try to figure those out. Yeah. And then rank them in order from most negative to most positive. And I will pop up a poll just so if you have your answer, feel free to just rank them from most negative to most positive. So we'll take a few minutes and do that. If you have any questions or you want to check anything, please do let me know. And it might be hard to see, but there are negative signs right here as well. So let me just make them a little darker for you. All right, so what I've done, and if you're still working, please do continue. But what I've done is I've just put over the numbers for oxygen and hydrogen, and this will make it go a lot faster after you do that. So B overall has a -1 charge, therefore this carbon has to be +3, has 2 hydrogens, so -2 for that carbon. Same thing over here, +3. So overall, this is +4. C, this one's relatively straightforward since it's only hydrogens, no charges. So -3, -2, -3, 6. So C is -8. D, also relatively straightforward, -3, -1, -2. Overall, -6. And then E, -3 +2, then a +3. So overall +2. And so if I'm ranking them from most negative to most positive, so it goes C, D, A, E, and then finally B. And that's how you can figure out the redox state of just about every molecule we're going to look at in this class. We might look at some compounds with nitrogen, but very rarely are we going to deal with nitrogen. It's mostly going to be carbon, hydrogen, and oxygen. Right. So any questions about that? Seems like we got our poll correctly. All right, let's move on then. Now we're going to move on to our review of thermodynamics. How does energy change? Thermodynamics is a huge part of metabolism since we're dealing with the movement of energy and the storing of energy in compounds and the breaking down of compounds to release that energy and to build stuff. So some terms to remember from Biochem 1. We're going to be talking about Gibbs free energy, which is delta G. This not dagger, but this, I'm slipping on the word. So let's just call it not. This means biochemical standard state. So this symbol just means we're looking at the free energy when we're holding everything at a constant concentration in a constant temperature and a constant pH, right? So constant, and everything is 1 molar, right? Temp equals 37 degrees. pH equals 7. So this is a way we can compare energy between different reactions. And so if we look at our generic reaction, A plus B goes to C plus D, the free energy change of that reaction, our delta G, is equal to the delta G at standard conditions plus RT natural log products over reactants. And let's say our system's at equilibrium. And if you remember, equilibrium means the forward and reverse speeds are the same. This is a common confusion. Equilibrium does not mean concentrations are the same. All that means is that my forward reaction and reverse reaction are going at the same rate. And when that's true, delta G equals 0. And the ratio of products to reactants is now called KEQ. So KEQ is the ratio of products to reactants at equilibrium. And by doing minus RT, R is the gas constant, T is temperature, ln KEQ, that's how we can calculate delta G now. Right? Now, inside the body, many reactions we're going to look at are very near equilibrium. That means that all the concentrations are near their KEQ values, and the free energy of these reactions are roughly 0. And what that means for us is that metabolism, a lot of reactions in metabolism, not all, but a lot, are reversible, and they can go in reverse all the time. Therefore, to make sure we're going in the right direction, we need to control the amounts of substrates and products. And one way we can do that is by having a couple reactions be very far from equilibrium. That is, when you look at metabolism cycles, a few key reactions are very far from equilibrium. They are irreversible. They only go one way. And by having these irreversible reactions, you drive the whole system forward. So when we look at glycolysis, there's 10 reactions. 3 of them are irreversible. So those 3 help to push the whole system forward. And that's something we will see a lot when we look at these cycles. A couple irreversible, most are reversible. So any questions about the ideas presented on this slide? Actually, quite a bit of information presented here. All right. If not, and if you are, still feel free to type, but if not, we'll move on. So here's a question for you. So the top is the information we just covered. So we're going to look at a specific reaction in this question. And the question starts there with the font is a little smaller. So citrate synthase will catalyze the following reaction of oxaloacetate plus acetyl-CoA makes citrate plus HS-CoA. Now, the standard free energy for this reaction is minus 31.5 kilojoules per mole. With that information, what is the equilibrium constant at 37C if given the gas constant? Then, based on your KEQ, so remember, equilibrium constant means KEQ, if my concentration of citrate is equal to my concentration of AS coenzyme A, therefore, for every 1 oxaloacetate molecule I have, how many citrate molecules must there be? And C, let's say delta G is minus 15 kilojoules per mole. What is my ratio of products to reactants? Right, so math time, a little early math for us in the semester. See if you can work your way through some of these thermodynamic problems. If you have questions or if you have answers you want to check with me, let me know. I'll give you a couple minutes to work on this and then I'll come back with the answers. All right, I'm going to begin working through A, in case you're a little stuck there. So the first thing we want to do is declare our variables. I already did that for KEQ. That's what we're trying to find, right? Standard free energy change. That is delta G, not prime. That's the word I was looking for, not. Or actually, I was looking for the word prime. So delta G, not prime, is that. So we're going to be using this equation for A. So minus 31.5 kilojoules per mole equals minus R. So I give you R in joules. Make sure all your units match on both sides of the equation. So I have kilojoules right here. I need to convert R into kilojoules. Hopefully you remember that there are 1,000 joules for every 1 kilojoule. So R is 8.314 times 10 to the minus 3 kilojoules per Kelvin times mole. And our R constants in Kelvin, our temperatures in Celsius. So we need to put that in Kelvin as well. And that is C plus 273.15 equals K. So that would be, I'm just going to put it as 310. It would be 310.15, but when I did this calculation, I just did 310 times the natural log of KQ. All right, so the first thing we want to do is get natural log of KQ alone. Just as a reminder, anything that is having a natural log done on it, we can't do anything to it mathematically. So think of natural log and everything that follows it as a unit. You cannot break that up yet. But what we can do is we can divide each side by R and T. And what we get is 12.22 equals the natural log of KEQ. Then to get rid of a natural log, you take the exponent of each side. So that's E caret on your calculator. So I do the exponent of this side. I do the exponent of this side. Natural log and exponents cancel out. And so KEQ equals E to the power of 12.22. So KEQ is roughly equal to 203,191. If you got like a slightly different answer, 202, something like that, that's fine. I think I did either I did or didn't do rounding. I forget which one, but any difference there that you might get, if it's around 203,000, it's probably just due to the way I rounded things. All right, so that is KEQ. One thing I want you to be aware with KEQ is what the numbers mean again. So if KEQ is greater than 1, that means products are favored. You're going to have more products than reactants at the end of the reaction or at equilibrium. If KEQ is less than 1, reactants are favored. If it equals 1, then the concentration of products and reactants will be the same. All right. So that's A. Any questions about the math there? All right. So B is kind of tricky to think about. It's kind of tricky to even know what I'm asking for B, right? What does it mean to favor products or reactants? That means when we hit equilibrium, and remember at equilibrium, the reaction speed of the forward and backwards reactions are the same. So my forward reaction speed and my reverse reaction speed are going at the same rate. Well, if products are favored, that means I have more products at the time of equilibrium. If reactants are favored, that means I have more reactants at the time of equilibrium. And if it's the same, that means the concentrations are the same. That's what I mean by favored. What are you going to have more of at the time of equilibrium? All right, so B, what am I even asking? All right, so based on your KEQ number, which we just got, I want to know how many citrate molecules are there for every one oxaloacetate. So what I'm saying is that the concentration of oxaloacetate is 1, because I'm saying there's one of those. And I want to know how many citrates there are. And the concentration of citrate is the same as the concentration of HSCOA. And I guess I didn't say this, but I probably should have. Also use the concentration of acetyl-CoA as 1 as well. Technically, you could put like any number there and the ratio would still work out. It's a lot easier if you put it as 1. All right, so KEQ from our equation up here equals the concentrations of products, so the concentration of citrate, multiplied by the concentration of our other product, HSCOA, divided by concentration of reactants, oxaloacetate, multiplied by acetyl-CoA. All right, so KEQ, we have a number for that, 203,198. That is equal to, I'm going to call the concentration of citrate X. It's some number X. I don't know what it is. That's what I'm trying to figure out, but I'm going to give it a variable X. If citrate is equal to S, and I say HSCOA has the same concentration, this must also equal X. And I already said oxaloacetate and acetyl-CoA equals 1. So what you get is x times x over 1 times 1. Now it's just algebra, and I'm going to simplify it. So x squared, which I got from right here, is equal to KEQ, which we solved in A. 198. Solve for x. X equals, I think roughly, if I did my calculation right, 451. So what this tells us is that equilibrium, if you have a KEQ value of 203,000 and you have one molecule of oxaloacetate, you will have 451 molecules of citrate. That's the ratio of oxaloacetate to citrate at equilibrium, 1 to 451. Again, this is just demonstrating to us products are favored at big KEQs because we have way more product than we do of reactant. So questions about B. Really confusing to wrap your head around like what the question's asking, and I understand that, but hopefully once you see what I meant by that, then the math and the logic follows. And let's go to C. C is much more straightforward. All right, so C. What's the ratio of products reactants if delta G is minus 15 kilojoules per mole? So we want to use the equation that relates delta G to reactants and products, which is our equation I just put the C next to. So delta G equals delta G naught prime plus RT ln products over reactants. All right, so delta G is minus 15. Delta G naught prime, we already gave that in A, is minus 31.5 plus RT. Again, we want to be in kilojoules. So 8.314 times 10 to the minus 3 multiplied by temp. We're going to use the same temp as in A, 310. Natural log products, reactants. All right, so we have that. We want to get the natural log of products and reactants by itself. So we subtract each side by 31.5. So we're going to do this term first, subtract each side by that. Then we're going to divide each side by RT. And hopefully I did my math right. And you should get 6.402 equals natural log products reactants. Hopefully I did that right. Let me just double check. It's always good to double check your work. Plus 3 times 310, 6.4. Where did minus 15 for delta G come from? That's from the actual question, because I'm saying delta G is minus 15. All right, so once we have that, then we just solve for the relationship between products and reactants. So do exponent of each side again. Oh, you couldn't see that? Oh, yeah. So, yeah, that's what it says on the bottom there. Exponent, exponent. And when we do that, we find that the ratio of products to reactants is 603. So this is saying for every one reactant we have 603 products. And remember, this is just the this is citrate multiplied by HCOA. Don't need to worry about that last part since I was just asking for the ratio, but that's how you'd figure it out. And that's how you can use all these equations in thermodynamics to ask a bunch of different questions and solve for a bunch of different situations. All right, so looking at that lovely math, is there any questions on how I went through that? Place where you got confused or stuck. All right. Looks like we do have something. Just setting up B. Yeah, B is the most confusing because it's really confusing on what that question's even asking. So yeah, B is definitely the hardest because I'm putting into words what the mathematical equation says. And it's like where to put the one, what do you mean equals to equals? Hopefully working through B with putting an equation into words made a little more sense. You didn't get 6.402. I just redid it, and that's what I got again. What I will say is be careful of your parentheses. Because if you don't put in your parentheses correctly, I could definitely see you get the incorrect answer. But redoing it when I did it on Tuesday, I got 6.4 both times. So it's possible I did it wrong both times. Let me just plus 3.5. But I can't see any error at my part that's screaming out to me right now. So I will, I'll put up the answer sheet that will have like my more detailed notes. So hopefully you can follow through there. If you are still getting like not 6.4, what I want you to do is like maybe take an image of your calculator and send it to me by email, and I can take a look at it and see if I can spot anything that went wrong or further confirmation if I did something wrong. All right, but with that, we will move on to this idea of flux. And we talked about flux without naming it a couple slides ago, earlier today. But flux is how fast you're going through a pathway. And to really calculate flux, you need to know which enzymes are near equilibrium and which are the ones that are far away. Because remember, the ones that are far away from equilibrium, you can think of those as your faucets, right? You stop those reactions, you're turning off the faucet, you're stopping flux. You allow those reactions to go forward, you're turning on the faucet, flux increases. You're going through your different cycles there, right? And these enzymes, like I said, control everything. And so they have three important implications as shown here. So if they're irreversible, delta G is a big negative number, right? And that's what makes us go in one direction. When we look at these pathways, we will see that we have what's called a committed step. That is an enzyme that is irreversible very early in the pathway. So once you go through that enzyme, there's no turning back, because one of the themes of metabolism is that we use the same materials for a different number of pathways. And so once we're locked into a pathway, we don't want to go back to the common pool. You're going down this pathway. Your fate has been sealed. And to do that, we have an enzyme at the very beginning or near the beginning that makes a reaction irreversible. And catabolic and anabolic pathways differ. They have to. Remember, this is destroying and building things. Well, on our metabolism pathway, if we're breaking down something and we have an irreversible step, then we can't go back up that pathway. It's impossible. So if we do want to rebuild things, for example, if we want to rebuild glucose from pyruvate, we need a separate pathway. And we're going to look at that as well. But destroying and building pathways have to be separate because we have enzymes that are irreversible in each of these pathways. All right, so here is a question just for us to get our understanding of all the terms we went over today. So I'm just going to pop up the poll here. And here's a good example of a simple test question. If I want you to give me the definition of a near equilibrium reaction, what would you say? All right. Looks like we're all in. Looks like most of us got that. Has a free energy change near zero. That is correct. That is near equilibrium. Because remember, at equilibrium, delta G equals zero. So if you're near it, you're about zero. For the other folks who answered C, a control point is far from equilibrium, right? To control metabolism, these are the enzymes where delta G is like minus like big number, like in the teens, minus 20, something like that. Near equilibrium do not control flux. Now, how do we control flux? How do we control these far from equilibrium enzymes? We have a certain different methods that we're going to see pop up time and time again. The first is what's called allosteric control. And it's very cool how cells have set this up. But the idea of allosteric control is that a product that is made further down the metabolic pathway can go and inhibit an enzyme earlier up the pathway. Citrate is a prime example of this. Citrate is made in the citric acid cycle. What citrate can do is that it can go to the glycolysis pathway and inhibit glycolysis by knocking out an enzyme there. So citrate isn't made until much further down the pathway of glycolysis, but it's allosteric control. If you have a lot of citrate, you have a lot of energy. So citrate will go and inhibit your energy producing enzymes. Another way is covalent modification. This is almost exclusively done by phosphorylation. There are other examples such as methylation or acetylation. Just if you don't remember your chemistry, methyl group and acetyl group is basically that, right? But we use phosphorylation, and these are usually taken care of by kinases. Kinases can add phosphor groups, and lyases can take them off. But that is one way we can regulate enzymes. Phosphate that turns something on, dephosphorylate it and turn something off, or vice versa. Each enzyme reacts differently to a phosphate. We also have cycles. That is being shown here on the right-hand side. Here we have a reverse pathway and a forward pathway. So AB goes to CD, or DC goes to BA. And if you put enzymes here, so let's say this is enzyme 1, this is enzyme 2. They are different enzymes. You can control flux by changing the speed of enzyme 1 and enzyme 2, right? So do you want flux to go to D? Do you want it to go down the pathway? Speed up enzyme 1, slow down enzyme 2. Do you want to go the reverse way? Well, just do the reverse. Speed up enzyme 2, slow down enzyme 1. Again, we'll see this in effect when it comes to glycolysis. The last is the slowest, but it can have a big effect. Enzyme concentrations, right? Start making more enzymes or destroy the enzymes you already have. Genetic control. 1, 2, and 3 can happen in matters of seconds, milliseconds. 1, 2, and 3 are incredibly fast. Genetic control, you're looking on the order of minutes, tens of minutes sometimes. But these are all the ways that we can control flux in our cells. So any questions about those ideas? What do you, when you say speed up the enzyme, what do you mean? So by, you can do different things to it. One, you can inhibit it, or you could phosphorylate it, or it could be, yeah, so inhibit by allosteric control, or you could inhibit by like phosphorylation. And if you slow down like enzyme, so let's make, yeah, the rate changes exactly. But it's a little more complicated than that. So let's say, for example, you have 100 copies of enzyme 1 and 100 copies of enzyme 2. And they go at the same exact speed. So the speed of each individual enzyme 1, their rate of reaction. So I guess I should stop using speed and say rate of reaction, is the same as E2. Their rate of reactions are the same. So to change this, because right now we're in equilibrium, and if I give you this situation, we're not making A or D. We're just doing a useless cycle where we go to B and then we go from B to C, right back to B. You're just doing a circle and you're wasting time. You're not making anything. So to change that, what I can do is that I can inhibit like 90 E1 molecules. So if I inhibit 90 E1 molecules, then I have 10 E1s and 100 E2s. So in effect, I slowed down the rate of my forward reaction just because I stopped the majority of the enzymes. And now my reverse reaction is going much faster. In glycolysis, it's really cool how it happens, and we'll see that, where it's really like one enzyme that has 2 different locations on it. Like one does the forward reaction and the other location does a reverse reaction. And we just kind of like specifically inhibit a part of the enzyme. Like this one part that takes care of E1, you are inhibited without touching E2. But that's basically what I mean when I say speeds. Whenever I say speed, it means rate of reaction. Any other questions about controlling flux? All right. So here are just some more basic questions. A very basic question, actually. I think I have a poll for this. So let me pop that up. Based on the information presented here, oxyl acetate plus acetyl-CoA goes citrate plus HSCOA. Standard free energy is minus 31.5. Based on this information alone, do you think citrate synthase is a control point for the citric acid cycle? Imagine you knew nothing about the citric acid cycle and I just gave you that piece of information. Would you say that's a control point or not? Give like 15 more seconds for you to think that over. All right. So the answer is it is a control point. So yes. So hopefully when we go through this class and we start looking at the thermodynamics of metabolism, you will start to get a better sense intuitively of delta G values. Because I'm sure up to this point in your careers, if I said a delta G of minus 31 versus a delta G of minus 5, that might not sound like a lot to you at all. But once you get a sense of these things, that's a huge change. So when you're looking at delta G, something that's like minus 20 or above, even like minus 15 or above, that's a huge number. That's irreversible. Minus 31.5, that is massive when it comes to enzymes, right? We're not going to see enzymes that often that work at such a scale, right? To give you a sense, and we're going to look at this maybe today, if not Tuesday, going from ATP to AMP, that's roughly minus 46, right? And that's a lot of energy. So we have an enzyme that's going at minus 31. So that's very big, irreversible. So yes, it is. That is a control point. Right, that ends this lecture. So let's pop up the next one. All right. Where we're going to talk about more math. Control points are the path of no return points. Control points, yes, are irreversible, but there's usually only one control point that is the point of no return. And honestly, we're going to look, there's always a way to get around that. Even though we have what's called committed steps, you can go in reverse as long as you use a different enzyme. But for right now, the enzymes themselves are irreversible. So if you want to go in reverse, you need to find a different enzyme. That's the most succinct way I can put it. They are basically means point of no return just because you can't go backwards using that system. And they control flux. All right. So we're going to continue to talk about energy. And in our first reaction, we have glucose. Glucose plus oxygen makes carbon dioxide and water. That's glycolysis right there in a nutshell. You make negative 2,850 kilojoules per mole. We just said minus 31 is massive, like minus 2,850. That is a lot of energy for you to use. if you want to talk about like a fat, a C16 fat right here, that's minus 9,781 kilojoules to make carbon dioxide in water. And if you were ever wondering why we breathe out carbon dioxide, this is the reason. We take that sugar and fat and we make it into carbon dioxide in water. Now, if we broke down these molecules in one step, we would release all that energy at once. And we don't want to do that. We need to harness this energy. We need to trap this energy so we can use it. So metabolism is the breakdown of these molecules in many steps, allowing us to capture this energy. And we capture this energy in the form of molecules: ATP, NADH, FADH2, NADPH, FADPH2. We have a lot of molecules that we can use as energy sinks. And you can think of this as currency, ATP, NADH. We break down these higher structured sugars and fats to create cash. We then use this cash to build stuff or make stuff. So we store energy, then we use that energy to be alive, to make our proteins, to make our own lipids, to make anything in the cell. We need to spend energy to make it. Because remember, the law of conservation of energy, we cannot create energy. We also can't destroy it. It's constant, so we just use it. We take energy from a sugar and we use it to build our own stuff. So some terms we need to know, and I'm going to just answer these for us. This is, again, review, but these are going to pop up through our talks this whole semester. So an exergonic reaction, X, think of that as exit. We are releasing energy. And when we release energy, delta G is negative. N, I always think of that as in. Energy is going into something. That means our process is absorbing energy. That means delta G is positive. Gibbs free energy, we've been using it in the last two terms, delta G. The actual scientific term is ability to do work. So that's what that's what free energy is. It's your ability to do work. It's your money. It's you spend it to make stuff happen. Entropy, chaos or disorder. We give that term a delta S. Enthalpy is heat. We got that delta H. And our main equation, or one of our main equations that relates these two, is delta G equals delta H minus temperature multiplied by delta S. So we can think of energy in two forms. We can think of it as heat or disorder. And together, depending on what temperature we're at, we know how much work we can do. Or we know if a process will release energy or if a process will store energy. N can also be enter. Yeah, that's also a good way to think about it. It's entering us. Or entering the process, really. All right. So a little more review. And this one I will answer, but in a minute or two, because I want you to think about this. And we talked about this. This was like one of the last topics of Biochem 1, enzymes. So how does an enzyme change delta G naught prime? And how does delta G naught prime or delta G relate to reaction speeds? So take a minute, see if you can recall that information, and I will let you know the answer in a minute or two. But I want you to give it a good stab. Okay. So you know that enzymes lower the activation energy. So does it lower delta G, not prime? No. So um, no effect. So let's remember. So here, let's say that's our regular reaction coordinate. This is reactants. That's products. This is delta G. And so the difference between those two heights is delta G, not prime. That's the free energy of a reaction. And let me get a different color here. All enzymes do is lower the activation barrier. So an enzyme will lower this delta G double dagger, if you remember those terms. So it has no effect on the free energy of a reaction. And this is thermodynamics, the energy of reactions. The rate of a reaction is called kinetics. How fast are you going? They have nothing to do with each other. If you know the delta G of a reaction, you cannot tell me how fast it goes. Give you two examples. So like iron plus water and oxygen forms rust, right? Delta G is negative for this reaction. It takes a long time though. Like if you put a nail outside, it will take quite a while for that to rust, even though it's spontaneous. Another example, balloon full of balloon full of air plus poking a hole in that balloon equals flat balloon. Can't spell balloon. That happens very fast. That also has a delta G of minus. They're both spontaneous reactions, but they go at different speeds because thermodynamics and kinetics are not related whatsoever. So common trap I see is students will look at delta G's of our metabolism enzymes and see the ones with the big negative signs and think they go faster. They don't. You cannot tell me the speed of anything by delta G. So that's a little refresher on enzymes there. Now let's look at some of our energy molecules we'll be looking at this semester. The main one being ATP. There's ATP on the left is adenosine plus 3-phosphate. So adenosine triphosphate. You knock off one phosphate, that's ADP. You knock off another phosphate, that's AMP. They're connected by what are called phosphoanhydride bonds, right? And the way we get energy from these molecules is that we break off phosphates. Now, this is a giant misconception that you have been told, or you might have been told, I'm not sure actually, all throughout your biology / maybe chemistry career. When we break down ATP, you just don't release it into water, right? That's not how you get energy from ATP. You just don't break off a phosphate and magically get energy. That's not how ATP works, right? If you just broke off a phosphate in an enzyme and didn't do anything with that phosphate, you're probably not going to do any work. It's just going to fly off and you'll say bye-bye phosphate. The way ATP normally works in the body is that you take the phosphate from ATP and you stick it on something. And that is shown here on the right. Here we have a table of phosphate hydrolysis. Basically, how much energy do you get when you remove a phosphate? And the idea is that you take a high energy compound like ATP and you stick that phosphate on something else like a fructose or a glucose, which has a lower free energy. And it's that free energy difference that allows us to do work. And this whole idea, we're looking at phosphoryl group transfer potentials. That is, how much energy do I get out by taking a phosphate from a high energy compound to a low energy compound? And all of these compounds shown here on this table, they just don't break down by themselves. If you have ATP in a glass of water, that ATP isn't going anywhere. You're not going to spontaneously lose phosphates. You need some enzyme to help speed up that reaction. So enzymes are almost always needed to remove phosphates. Something else interesting, you can see that there's a couple compounds above ATP. So ATP is not the most negative phosphate compound we have. There's other ones, 1,3-bisphosphoglycerate, phosphoenolpyruvate, PEP, creatine. Those of you who like to work out and like to take creatine powder, creatine is basically a phosphate compound. That's higher energy than ATP. So yeah, there are a lot of different phosphate compounds in our body. And the way we get energy is just by moving phosphates to lower energy compounds, ATP being the most ubiquitous. Now, why are these compounds so high energy? This is straight up chemistry, straight up physical chemistry. It has to do with resonance structures, electrostatic repulsions, and solvation energy. So let's just go over these terms. Resonance structures, if you remember from organic chemistry, it's different structures or different ways we can manipulate bonds inside a structure. So these oxygens that oxygen rather is negatively charged. This is a bond. And so the resonance structure is either the oxygen on the bottom can be negative or the oxygen at the top can be negative. So that's an ATP. Well, if you have the phosphate get kicked off, we can have another oxygen be available for our negative charge. So when you break down phosphates, so if you go from like a triphosphate to inorganic phosphate plus diphosphate, you increase resonance structures by doing that. And the more resonance structures you have, the lower the energy of that compound. You are making that compound more energetically favorable. So lower resonance structures, higher energy when it comes to charged compounds. Electrostatic repulsion, you're in ATP, you're putting 3 negative phosphates right next to each other. They're very highly negative. They don't want to be near each other. So when you separate them, as shown up here, you are separating that charge. That's good. You lower the energy of your system. And solvation energy. What is solvation energy? Solvation energy is the ability for water to surround your phosphate, right? So phosphates are negatively charged, and so they want to be near the hydrogens of water. Hydrogens are partially positive, and so they balance each other out. If you're in the triphosphate form, you can fit less water than if you were in the diphosphate, form plus 1 phosphate that's been broken off. I can now put more water around these 3 molecules when they're in this form versus the top form. So by having the water surround my phosphates better, I have better solvation energy, and the energy of my compound becomes lower. So that is how, on the previous page, we had those phosphate energies. Whoops, sorry. That table 14.3. The more negative you are, the worse resonance structures you have, and the worse your solvation energy. The more positive your numbers are, the better resonance structures you have, the better solvation energy, less electrostatic repulsions. All right. Any questions about our terminology or what makes a phosphate compound high energy? All right. So here's a question. One I didn't talk about yet, but this is one of those critical thinking questions. See if you can think outside the box and connect everything you've learned from your various hours of studying different subjects. Why don't cells use heat to do things? We generate heat all the time. Our bodies are very hot. Why can't we use heat as a source to do work? Because in our free energy equation, heat is part of it. There's heat right there. Why can't we use that to do work? Too much heat will denature proteins. That is correct. But let's say I give you a small amount of heat that won't denature proteins. I would still say you can't use that to do work. But you are correct. Why? And maybe along those lines, why does heat denature proteins? Because the reaction needs specific temperature ranges. That kind of goes along with the same idea of heat denatures proteins. Because if you're outside the temperature range, your protein wouldn't work. So it's along those same lines, but I'm looking for kind of a bigger picture answer. Too chaotic. Is heat too chaotic? Yes. What do you mean by chaotic, though? High entropy. Heat and entropy are related, as in the delta Gibbs equation. What does high entropy mean for a protein? The protein has a lot of entropy. Yeah, this is one of those brain teasers. So let's think about this. We just talked about phosphates on the previous slide, and we said we can use phosphates as energy sinks to do work. What is it about the phosphate itself, that ATP molecule, that allows us to do work? Why is that such a good energy source? And why is heat not a viable energy source? And maybe along those lines, if you're cold, what does your body naturally do to warm itself up? Bond energy has to do with it. Shiver, shake. Yes. Okay. So we're going to step back and talk fundamental physics here. Heat is the energy of motion, right? The more motion you have, the more heat you have, right? And that's basically what heat is. The slower something is, the colder it is. The faster or more movement it has is the hotter it is. Okay. Now, thermal energy, we can't really use the big thing is capture and movement of energy. And you were all correct in what you've said about heat so far. I'm just trying to direct it into more coherent thoughts, like a thread of logic, right? So to use energy, we need to be able to capture it and like hold it and release it when we want to, right? We have to have full control over it. That's what's great about phosphates, right? So in our triphosphates, we have these three very high energy bonds. These are our energy. This is our energy storage. When we break those bonds and move a phosphate somewhere else, we are lowering the energy of that bond, and we are using that energy difference to do reactions, to do chemistry. If you just tried to do heat, all you would do, one, we can't store heat. Heat just dissipates because it's motion. But if for some reason you did get like an infusion of heat, as was pointed out, all that would do is would make your enzymes vibrate faster. Vibrations lead to an increase of entropy, which would ultimately unfold your proteins. So the main issue with heat is you can't really capture it. And two, heat is motion, right? We need chemical energy. We need energy in the form of these high energy bonds that we can control at any given time, move those phosphates around to lower energy compounds, and that energy difference allows us to do work. That is biothermodynamics in a nutshell. So higher the energy, the higher the kinetic energy, because phosphates have higher energy bonds. So energy, kinetic energy is thermal energy. The energy of bonds, we call that potential energy, right? While heat is more like kinetic energy. So since bonds have these potential energies, once we move the phosphates around, we're unlocking that potential energy to do work. Heat just makes stuff vibrate. Can't capture heat, and the second reason is that heat is more, if I use more scientific words, is kinetic energy. It's the energy of motion. We can't direct motion in such a way for chemistry to happen. Motion from heat is more or less random. You can't give a protein heat and want it to work a specific way. You can take a phosphate from ATP, put it on a specific point of the protein, and have that protein react a certain way due to the energy change and the charges you just put on. But you can't do that with heat. Again, that type of question is a very, the phrase is critical thinking question. It's one of those that you have to take a lot of information from various classes and try to meld it together. But that is why we use ATP and not like just random heat sinks. That's why we don't use brown fat to do all our processes, right? Brown fat is the fat we use to create heat. It's in a lot of babies since they're small and tiny. We use that to make heat at all. We don't use brown fat to really do reactions. Right. And that is all the time we have for today. I will put up a homework for the math portion of this. And then on Tuesday, we will continue talking about our phosphates, some Nernst equations, and we'll move on from there. If you have any questions about anything we did today or any of the homeworks when you look at it or getting to the homework, do not hesitate to send me an email as always, or you want to set up an appointment, that's fine with me too. Otherwise, hopefully I'll see you all on Tuesday and have a good weekend. Take care, everybody.